Okay, continuing with the evolution of the atomic theory and counting atoms, this is part 3. All right, atomic mass units. If you wanted to know the appropriate unit for finding the mass of a car, you would use kilograms. Cars are very, very big. The appropriate unit for finding the mass of a paperclip, paperclips are really tiny, you would use grams. The appropriate unit for finding the mass of an atom, atoms are extremely small, you would use atomic mass units, abbreviated AMU. Just like with any other unit, there has to be a standard against which we define the AMU. In other words, a set standard that everything is compared to so that we can have something to relate it back. For atomic mass units, that standard is carbon-12, the specific nuclide of carbon, meaning a specific isotope. Carbon-12 has been assigned exactly 12 AMUs. 1 AMU is exactly 1/12 the mass of 1 carbon-12, or 1.6605 times 10 to the negative 27 kilograms. It's a very small number. Much easier for us to say that 1 AMU is exactly 1/12 the mass of 1 carbon-12. Okay guys, let's take a look at atomic mass numbers that are not whole numbers. In looking at chlorine, we have this mass of 35.5. Well, we know that we can't have a 0.5 for a neutron. We need the whole neutron. Okay, we can't have half of a neutron. So we have to figure out, where is this 0.5 coming from? That has to do with the isotopes. Again, isotopes, the same element, different number of neutrons. If the neutrons change, then you have a different mass number. We have chlorine 35, atomic number 17, and then we have chlorine 37, still atomic number 17. Sometimes they will write with a mass number on one side and then put the atomic number on the other side of the symbol, depending on the word processing program that's being used. So how do we figure out the average atomic mass when looking at isotopes that are in our sample? So I have 2 different isotopes here. How would we figure out that average atomic mass? We're going to take a look at an example. To calculate average atomic mass, you would take the sum, this represents the sum, where you would take the percent of an isotope, multiply it by the average atomic mass of that isotope, and you would do that for all of your isotopes. So if you had 3 isotopes, you would have 3 separate calculations added together and then divided by 100. Let's take a look at an example. Boron has 2 isotopes. I have boron 10, which has an 10.013 atomic mass units, and boron 11, which has 11.009 atomic mass units. Now, you're wondering, okay, how is it possible that the isotopes have decimals in them? That has to do with looking at some other factors involved with the binding of the particles. We're not getting into that. This information would always be given to you. They have the abundance 18.7% and 81.3% respectively. When you see this respectively given, it means that you're looking at these in the same order that they're given. So this 18.7%, that's going to go with boron 10 because that was the first one given. This is the first percent given. And then the 81.3%, that's going to go with boron 11. That's the second percent given. This is the second isotope given. So to calculate, we're going to take the sum of the percent times the average atomic mass. So our first percent, 18.7. We're going to multiply that by the average atomic mass of the isotope. Well, that one was 10.013. But remember, we use to the hundredths place. So 10.01. We're going to add to that, that's the sum of, we're going to add to that the second isotope, which has a percent of 81.3, times its average atomic mass, which in this case is going to be 11.01. And this is all divided by 100. So when you punch this in on your calculator, the 18.7 times the 10.01, that's going to give us 187.187 plus the 81.3 times 11.01. That gives us 3. Do not do any rounding along the way. You must keep all numbers that are in your calculator, and you do the rounding at the very last step. And then this is all divided by 100. So when you add these two together, you're going to get all divided by 100. When you divide that by 100, you're going to get 10.823. Again, we record our atomic mass units to the hundredths place, so we would have 10.82 AMU. Again, to solve that, you take your percent for the isotope times that particular isotope's atomic mass unit. You're going to add that to the percent of a second isotope times its atomic mass unit, or your average atomic mass, all divided by 100. Okay, let's take a look at an example. We have a sample of carbon. There's 98.9% carbon-12, 1.1% for carbon-13, and an extremely small trace amount for carbon-14. They don't give us a percent amount for carbon-14. That's telling me that it is such a small amount, it's not even going to impact our answers, so we're not using it. For carbon-12, I'm going to go ahead and divide my percents in the beginning. Just move your decimal place 2 places to the left where you have 0.989, and that's times 12.00 times your atomic mass units. And then our second isotope, again moving the decimal to get rid of the percent, that's going to be 0.011 times 13.00. Now I'm not dividing by 100 because I've already divided the percents by 100, so that's already been taken into account. So when you would punch this in on your calculator, you would put 0.989 times 12 plus 0.011 times 13, and you would end up getting 12.011. Re-record our atomic mass units to the hundredths place, 12.01 AMU. If you don't like dividing by 100 at the beginning, you can leave it and keep your percent. You could still say 98.9 and 1.10. and then divide your final answer by 100 if you'd like. Now I have one for you to try. I am going to give you the final answer, 69.73 AMUs. You guys go ahead and solve that one, see if you can get it, and bring it to class, and we'll take a look tomorrow.